Okay, well, now that we've covered that fundamental preliminary material, we're ready to actually start working on learning the specifics of SN2 reactions. Now, to get started, let me ask you a question. How many steps are there? How many steps are there in an SN2 reaction? How many steps in an SN2 reaction? The answer is that there is one step. One step in an SN2 reaction. This is one of the first things you have to memorize about an SN2 reaction. So notice that in a way this is an unfortunate name. This is an unfortunate name because it has the number 2 in the name. The number 2 might trick you into thinking that there's 2 steps, but there isn't. Despite the number 2, there's only one step in an SN2 reaction. Why does this have the number 2 in its name? Well, maybe we'll get a chance to discuss that later, but an SN2 reaction is one step. So clearly what we have to do is we need to learn what happens in that one step. What happens in the one step of an SN2 reaction? Well, at this point, it'll be useful for us to look at this handout. Here's a handout that covers SN2 and other types of reactions as well. There's a link to this handout in the video description box. So now would be a good time to go to the video description box and click that link and print out this handout. I hope you'll have this in front of you for the rest of this video series. So what we need to focus on is what happens in an SN2 reaction. So here we want to study an SN2 reaction. And remember that there is one main step. I said one main step here because there are some SN2 reactions that besides the main step might also have an additional acid-base step. So what we should really say is that there's one main step in an SN2 reaction. And what happens in the main step of the SN2 reaction is this. The nucleophile joins the alpha carbon and the leaving group leaves the alpha carbon. The nucleophile joins the alpha carbon and the leaving group leaves the alpha carbon. So notice that means that really there's two things that happen in this one step. The two things that happen are that the nucleophile joins the alpha carbon and the leaving group leaves the alpha carbon. By the way, now you can start to see why we had to cover all that fundamental material about nucleophiles and leaving groups and alpha carbons before we were ready to start studying the specifics of an SN2 reaction. So we've learned that there is one step in an SN2 reaction, and during that one step, two things happen. The nucleophile joins the alpha carbon, and the leaving group leaves the alpha carbon. Okay, well, here's a problem for us to try. We need to draw the mechanism and the product for this SN2 reaction. You might want to pause the video and try that on your own if you've learned a little about SN2 in class already. But now let's go through this reaction together. Now the first thing I'm going to do is identify the roles that I expect atoms to play. Or maybe the very first thing I'm going to do is number these carbons so we can refer to them specifically. By the way, we are not going to be using these numbers for IUPAC naming. We're just going to use these numbers for our own personal reference. And therefore, we don't need to worry about whether we should number from left to right or from right to left. We're not using these numbers for naming, just for our own personal use, to refer more specifically to the carbons. Now let's identify the roles that we expect atoms to play. And remember, the atom that we want to especially focus on is the atom with the formal charge. Well, we see this atom with a formal charge, a negative bromine. This is likely to be a nucleophile. Atoms with negative charges are likely to want to donate electrons. Here we see a neutral chlorine. Since this is a neutral chlorine, this is likely to be a leaving group. Notice the big difference between an atom with a negative charge and a neutral atom. And the chlorine is going to make carbon 2 have a delta positive charge. We discussed in the previous video that chlorine is further to the right than carbon in the periodic table. So chlorine is more electronegative than carbon. So chlorine wants electrons more than carbon. So the chlorine will pull the electrons in this covalent bond closer to itself and further from carbon 2. And when we pull the negative electrons further from carbon-2, that gives carbon-2 a partial positive charge. It also gives the chlorine a partial negative charge, but we don't really care that much about this partial negative, so I won't be drawing that for the problem. We learned in the previous video that an atom with a delta positive charge is likely to be our electrophile. Because of the delta positive charge, we expect carbon-2 to be our electrophilic atom. So here we have used each of these clues that we learned about in the previous video. We learned that a negative formal charge is a clue for the nucleophile. A delta positive charge is a clue for the electrophilic atom. And we've memorized that neutral chlorine, bromine, or iodide are good leaving groups. Here we're talking about neutral formal charge. A chlorine with a neutral formal charge, we've memorized, is a good leaving group. Now, how do we use these roles to draw the actual electron-pushing arrows for the mechanism? Well, let's use what we've learned about what happens in the one step for an SN2 reaction. In this step, the nucleophile is going to join the alpha carbon. So we better label the alpha carbon. Remember that at the end of the previous video, we learned that the alpha carbon is the carbon attached to the leaving group. We're going to define the alpha carbon as the carbon that's attached to the leaving group. So we want this nucleophilic atom to join this alpha carbon. So how do we draw the electron-pushing arrows for that? Well, remember that every electron-pushing arrow has a head and a tail. So how do we draw the head and the tail of the electron-pushing arrow to show the nucleophile joining the alpha carbon? Should this nucleophile go at the head or the tail of an electron-pushing arrow? Well, we know that a nucleophile should go at the tail of an electron-pushing arrow, because remember that a nucleophile is an electron donor. The nucleophile wants to donate electrons, so it goes at the tail of an electron-pushing arrow to show that the electrons will be moving away from the nucleophile. The electron-pushing arrow shows the direction of movement of the electrons. The electrons are going to move away from this nucleophile so that the nucleophile can donate electrons. And who should go at the head of the arrow? Well, we know that the nucleophile is going to be joining the alpha carbon. That means that we have to put the head of the arrow on the electrophile, which is the alpha carbon. We draw the head of the arrow here to show the nucleophile joining the alpha carbon. Now notice that this electron-pushing arrow is consistent with what we learned in the previous video. In our previous video, we learned that the electron-pushing arrow should point from the nucleophile towards the electrophile. From the nucleophile towards the electrophile, and we've followed that with this arrow. This arrow points from the nucleophile towards the electrophile. The arrow shows the movement of the electrons from the nucleophile towards the electrophile. It shows the movement of electrons. It's an electron-pushing arrow. So the nucleophile is donating electrons to join the electrophile, which in this case happens to be the alpha carbon. And the electrophile is receiving electrons to join the nucleophile, which in this case happens to be the bromide. One of the things that happens in an SN2 is that the nucleophile joins the alpha carbon. And to show the nucleophile joining the alpha carbon, we draw an arrow from the nucleophile, the electron donor, towards the alpha carbon, which is the electrophile, our electron receiver. So now we know how to draw the electron-pushing arrow to represent this event. Now, notice that there is something else happening in this SN2 reaction. Something else that's happening is that the leaving group has to leave the alpha carbon. The leaving group has to leave the alpha carbon. That's going to happen in the same step, so we need to draw an arrow showing that. And we've already predicted that this is the way, in the previous video we saw this is the way you draw the arrow for a leaving group. Here's the way we draw the arrow for a leaving group, so I can draw that in here. Here's the arrow to show the leaving group, the chlorine, leaving the alpha carbon. This is a logical arrow because a leaving group is supposed to receive electrons. So the leaving group should go at the head of an electron pushing arrow to show that it's receiving electrons. And the tail of this arrow goes on the bond. That shows that we're going to be breaking the bond between the alpha carbon and the chlorine. That shows that the chlorine really will be leaving the alpha carbon. We're breaking this bond, so the chlorine really is leaving the alpha carbon, and as it leaves, the chlorine will be taking the electrons from the bond. So here's the general way to draw the arrow for a leaving group, and we've illustrated how to apply that to this leaving group. I'm going through all of these steps very slowly right now to make this as clear as possible, but obviously eventually you need to have practiced this sufficiently so that you can draw these arrows much more quickly and efficiently than the time it takes me to discuss them right now. So we've used this rule and this rule to draw the arrows involving the nucleophile, electrophile, and leaving group in the SN2 reaction. We use this rule to show the nucleophile joining the electrophilic alpha carbon. And we use this rule to show the leaving group leaving the alpha carbon. For an SN2 reaction, the particular atom that the leaving group is leaving is the alpha carbon. You should have memorized that the two things that happen in the single step of an SN2 reaction is that the nucleophile joins the alpha carbon and the leaving group leaves the alpha carbon. And here's how to draw the electron pushing arrows for those things that happen. Remember in the previous video that we also learned that at the beginning of the series of arrows, you should put a negative or neutral atom. In the middle of the series of arrows, you should put a neutral atom. And at the end of the series of arrows, you should put a positive or neutral atom. Do you see how we followed that pattern here? We had a negative formal charge here, so we put the atom with the negative formal charge at the beginning of the series of arrows. And in the middle of the series of arrows, we put carbon 2, which has a neutral formal charge. We put carbon 2 with a neutral formal charge in the middle of the series of arrows. As we discussed in the previous video, don't confuse formal charges with delta charges. It's perfectly okay to have a delta positive in the middle of the arrows. Here we have a delta positive in the middle of the arrows, but the formal charge on carbon 2 is neutral. We want to put an atom with a neutral formal charge in the middle of the series of arrows. It's okay for there to be a delta charge in the middle. Now notice that none of these atoms had a positive formal charge. Oftentimes it would be best to put an atom with a positive formal charge at the end of the series of arrows. But because none of these atoms had a positive formal charge, we did the next best thing and we put a neutral atom at the end of the series. Here we put an atom with a neutral formal charge. We put an atom with a neutral formal charge at the end of the series of arrows. Of course, we know this atom has a delta negative, but this is about formal charges. We put an atom with a neutral formal charge at the end of the series of arrows. Remember that we would never, or almost never, put a negative atom at the end of the arrows. We would almost never put an atom with a negative formal charge. We would almost never put an atom with a negative formal charge at the end of the series of arrows. Instead, this atom with a negative formal charge goes at the beginning of the series of arrows, and in this case, we put an atom with a neutral formal charge at the end of the series of arrows. So this SN2 reaction is consistent with these rules that we learned in the previous video. The most important tool for making sure that you draw the correct arrows is using the formal charges. The most important thing here is to make sure that our formal charges are beginning on the atom with a negative formal charge. So I hope that now you have a better idea of what are the two main things that happen during an SN2 reaction. The nucleophile joins the alpha carbon, that's shown with this arrow, and the leaving group leaves the alpha carbon, that's shown with this arrow. Since there are two things happening in the SN2 reaction, we have to draw two electron pushing arrows in this step. Keep in mind that both of these things happen simultaneously in the same step. Now that we've finished drawing the electron pushing arrows for this step, it's time to actually draw the product of this step. Here is a method that we can use for drawing a product, based on the electron pushing arrows. This is a simplified method. As you get to more complicated mechanisms, we'll need to complicate this method, but for the time being we can use this simplified method. I encourage you to always number all the carbons. I've already done that. I've numbered these carbons. And now we have to look at each of these arrows, and for each arrow we have to erase a bond or draw a bond or both. So do you think this arrow tells us to erase a bond or draw a bond or both? Well, I hope it's clear to you that this is an arrow that tells us to draw a bond between the bromine and carbon 2. I hope it's just intuitive that this is an arrow that tells us to draw a bond between the bromine and carbon 2. So I'm going to go ahead and do that. I'm going to draw that bond between the bromine and carbon 2. Okay. The other thing is that for the first arrow in the series, we need to change a formal charge. Because this bromine is losing electrons from this first arrow, the bromine should become one step less negative. The bromine is losing electrons, and electrons have a negative charge. So since the bromine is losing negative electrons, it becomes one step less negative. So I've already drawn this bromine as neutral. We make the atom that loses electrons from the first arrow one step less negative. And now we can just move on to the next arrow. So again, we're going to repeat these steps for the next arrow. So for this next arrow, we should either erase a bond or draw a bond or both. And I hope it's intuitive to you that this is an arrow that tells us to erase a bond. This arrow tells us to erase a bond between carbon 2 and the chlorine. And in fact, if you look, you'll see I've already erased the bond between carbon 2 and the chlorine. And because this is the last arrow in the series, we again have to change a charge. This chlorine started neutral, but it's gaining negative electrons from this arrow. If you start neutral and you gain negative electrons, you should become one step more negative. Well, one step more negative than neutral would make this chlorine negative. So we ended up changing two charges. We changed the charge on the bromine from negative to neutral, and we changed the charge on the chlorine from neutral to negative. Notice that I'm continuing to follow this advice of numbering all the carbons. So I numbered the carbons in this picture as well as in this picture. The purpose of the numbers is to show you which carbons are the same in different pictures. I numbered this carbon, carbon 1, to show that it was the same carbon as this carbon. And I numbered this carbon, carbon 2, to show that it's the same carbon as this carbon. So notice that it would be useless to call these carbons 3 and 4. It's pointless to call these carbons 3 and 4 because then you're not using the numbers to show how these two carbons are the same as these two carbons. So make sure that your numbers are consistent between your pictures so that the numbers will show you which carbons are the same in different pictures. And again, remember that we're going to be using these numbers for our own use, not for IUPAC naming. So you should not worry about whether you should number from left to right or from right to left. Number in whichever direction you feel is convenient. Remember that when you're drawing products, the most important thing to get right is the formal charges. How do you get those right? Well, you have to change some charges. You should always change two charges. Always change the charges for two atoms. Which atoms? The atom at the beginning of the series of arrows, like the bromine here, and the atom at the end of the series of arrows, like the chlorine. You never change the charges for any atoms in the middle of the series of arrows. We never change charges for atoms in the middle of the series of arrows. So for example here, we would not change the formal charge on carbon 2. Carbon 2 started with a neutral formal charge, and carbon 2 still has a neutral formal charge in this picture. The atoms in the middle of the series never change their charge, and you can see why. Because every atom that's in the middle of the series of arrows is both gaining electrons from one arrow and also losing electrons from the next arrow. And those two things cancel out so that overall the formal charge doesn't change. That should help us to see why we never change the charges for atoms in the middle of the series of arrows, only at the beginning and end of the series of arrows. By the way, don't confuse the formal charges with delta charges. I'm not going to bother to write down the delta charge in this picture because I don't care about it. So don't confuse formal charge and delta charge. Carbon-2 started with 0 formal charge, but with a positive delta charge. Carbon-2 started with no formal charge, but with a positive delta charge. Now in this picture, there's still no formal charge, and we just don't care about the delta charge. I only wrote down the delta charge here to help me see why this would be an electrophile. I don't care what the delta charge is in this picture, although you could see this will still have a delta positive charge because it's still bounded to something that's more that's to its right in the periodic table. But I'm not going to bother writing that down because we don't care about the delta charge in this picture. So remember, these are the rules for changing the formal charges. These are not rules for changing delta charges. All right, so here's our two products for this reaction. I took my time and tried to explain in detail how to get these products from these arrows, but obviously with practice you want to get to the point where you can draw the products much more quickly than the time it took me to discuss the process for this problem. Here is a checklist of things that are very useful to carry out for every reaction as a beginning Ochem student. And you can see how we carried out each of these in this reaction. We numbered all the carbons in the starting material. We labeled which specific atoms were playing which roles, and we did identify the clues that told us which atoms would play which roles. The clue that the bromine would be a nucleophile was the negative formal charge on the bromine. The clue that carbon-2 would be the electrophile was the delta positive charge on carbon-2. And the clue that the chlorine would be the leaving group was simply that we have memorized that neutral chlorine is a good leaving group. Then we drew the electron pushing arrows. Be sure that you don't start drawing the products until you have finished drawing the electron pushing arrows. Don't begin drawing the products until you've finished drawing your electron pushing arrows. And then when we drew the products, we were careful to number all the carbons in the products, trying to use numbers that were consistent with the numbers we used for our starting materials. This is a good checklist to make sure that you carry out for every reaction that you're practicing as a beginning Ochem student. Okay, well, let's get some more practice with this reaction. Please pause the video and try to draw the mechanism and the product for this reaction. I hope you actually tried that on paper, and now let's go through that together. It's good to start by numbering all the carbons. So I'll number the carbons like so. Now we'd like to identify the roles that atoms will play, and we should start by especially focusing on the atom with the formal charge. When we see this negative formal charge, we expect that atom to be an electron donor, which means a nucleophile. Over here, we can see that bromine is to the right of carbon in the periodic table, so that's going to create a delta positive charge on this carbon. So we can say that carbon-3 has a clue that it's going to be the electrophile. I guess I'll write that over here. And we've memorized that neutral bromine is an acceptable leaving group. Notice there's a big difference between a negative halogen, which can be a nucleophile, and a neutral halogen, which can be a leaving group. Now we're ready to draw the electron pushing arrows for the mechanism in this SN2 reaction. Do you remember what happens in an SN2 reaction? There's one step where the nucleophile joins the alpha carbon and the leaving group leaves the alpha carbon. So it'll help to label that this is our alpha carbon. Remember, this is called the alpha carbon because this is the carbon that's attached to the leaving group. All right, well, remember that the electrons should start here on the nucleophile because the electrons want to move away from the electron donor. They should move towards the electron receiver, which is the electrophile, and a leaving group is also an electron receiver, and the arrow for the leaving group looks like this. Electron pushing arrows point away from a negative charge because electrons want to move away from a negative charge. Only now should we draw the product. Remember, don't start drawing the product until you've drawn all the electron pushing arrows. So draw both of these electron pushing arrows before you start drawing the product. Does this arrow tell us to erase a bond or draw a bond or both? I hope it's intuitive that this arrow tells us to draw a bond between the iodide and carbon-3. Notice that I'm going to automatically put numbers in on this product, making the numbers consistent with the numbers in the starting material. Also, because this is the first arrow, we need to change the charge at the beginning of the arrows. This iodide started negative, but it's losing electrons. So the iodide becomes one step less negative, which means it becomes neutral. Now, does this arrow tells us to break a bond. It tells us to break the bond between carbon-3 and the bromine, which I've actually already done. And also, because this is the last arrow in the series, this also arrow tells us to change a charge, to change the charge on the bromine. The bromine started neutral, and it's gaining electrons. So it should become one step more negative, so the bromine becomes negative. Remember that the most important part of the products to get right is the formal charges. How many charges should you change? You always change 2 charges for the mechanism step. And how do you know which 2 charges to change? You change the charge for the atom at the beginning of the series of arrows, the iodine here, and the atom at the end of the series of arrows, the bromine here. We do not change charges, any formal charges for the atoms in the middle of the arrows, like carbon-3. And let me be clear that these are all rules for the formal charges, not for the delta charges. Remember that we just don't really care about the delta charges in the product, so I won't bother drawing any delta charges in the product. Remember that we said here you should change 2 formal charges for the entire mechanism step. So keep in mind that both of these arrows are occurring in the same mechanism step. Both of these arrows are occurring simultaneously in the same mechanism step. So we're changing a total of 2 charges for both of these arrows. The charge on the iodide at the beginning of the series of arrows, and the charge on the bromine at the end of the series of arrows. This example gave us a chance to practice the idea that there is one step in an SN2 reaction, and 2 things happen in that step simultaneously. The nucleophile joins the alpha carbon, and simultaneously the leaving group leaves the alpha carbon. But why does the leaving group have to leave the alpha carbon? What would go wrong if the leaving group didn't leave the alpha carbon? Let's figure out what would go wrong if the leaving group did not leave the alpha carbon. Let's say this leaving group did not leave the alpha carbon. Can you see what goes wrong? Well, if the leaving group did not leave the alpha carbon, then the product would look like this. The leaving group bromine would still be attached to the alpha carbon after the iodide attaches. Do you see why this doesn't make sense? It's because carbon-3 in this picture already has 4 bonds. A neutral carbon already has 4 bonds. This carbon has a bond to carbon-2. Carbon-3 has a bond to the bromine. And you should know that carbon-3 also has 2 bonds to hidden hydrogens. 2 bonds to hidden hydrogens in order for this neutral carbon to have 4 bonds total. But then in this picture, if the leaving group didn't leave, we would be left with 5 bonds. Carbon-3 would be bonded to the iodide, the bromine, carbon-2, and carbon-3 would still be bonded to those 2 hidden hydrogens. Well, that would be 5 bonds total, and that's too many, right? A carbon can't have more than 4 bonds. It can't have more than a complete octet. So I hope this shows you why it's logical that it's logical for the leaving group to leave the alpha carbon. The leaving group has to leave the alpha carbon because otherwise there won't be room on the alpha carbon for the nucleophile. It's logical that the leaving group has to leave the alpha carbon in this SN2 reaction because otherwise there wouldn't be room on the alpha carbon for the nucleophile. That might not, you can only see that though if you remember that there might be hidden hydrogens on the alpha carbon, such as in this case where our alpha carbon had 2 hidden hydrogens. Notice that we carried out all the steps in this checklist. We numbered all the carbons in the starting material. We labeled the roles played by the specific atoms and identified the clues that helped us to identify those roles. The clue that the iodide will be the nucleophile is the negative charge on the iodide. The clue that carbon-3 will be the electrophile is the delta positive on carbon-3, and the clue that the bromine will be the leaving group is simply the fact that we've memorized that neutral bromine is a good leaving group. Make sure that you actually carry out this step of labeling the roles and identifying the clues, both because that will help you to correctly draw the arrows, and also because it will help you to internalize how to use these roles of nucleophile, electrophile, and leaving group, which is an absolutely crucial skill to develop as quickly as possible for your Ochem class. Then we drew the electron pushing arrows. We drew the products after we finished the electron pushing arrows, and we were careful to number all the carbons in the products consistently with how we numbered the carbons in the starting materials. Now remember, what is the name of this reaction? The name of this reaction is SN2. Let's discuss that name a little bit more. Do you know what the S stands for? You should know that the S stands for substitution. Do you see why this is called a substitution reaction? Who are we substituting for who? Well, we're substituting the iodide for the bromine. So this is called a substitution reaction because the nucleophile substitutes for the leaving group. And why does this have N in the name? Do you know what the N stands for? The N stands for nucleophilic. We can say that this bromine on the alpha carbon is going to be replaced. And who is the bromine on the alpha carbon going to be replaced by? It's going to be replaced by a nucleophile. That's, I guess, the logic behind saying that this is a nucleophilic substitution. I'm not really going to discuss yet why the number 2 is in this name. That this number 2 might be considered to be a little misleading because there's only one step in the reaction. Despite the fact that there's the number 2 in this name, there's only one step in the reaction. Remember, again, I'm calling this one main step because some SN2 reactions also have a acid-base helper step, but we're not going to have to get into that right now. But I'm calling this the one main step because some of the more complicated SN2 reactions can also have a helper step. But that's not relevant for these reactions that we're looking at right now. These reactions that we're looking at right now have one step total. So you should know that the S in SN2 stands for substitution and the N stands for nucleophilic. By the way, notice that in this reaction, I drew the nucleophile on the left and the electrophile on the right. Whereas in this reaction, the starting materials had the electrophile on the left and the nucleophile on the right. And I just hope that you see that it makes absolutely no difference. It makes absolutely no difference which molecule is drawn on the left and which is drawn on the right. We don't figure out the roles that things are going to play based on whether they're on the left or the right. We figure out the roles based on the clues that we've talked about, such as which atom has the negative charge. Well, we've now learned the most basic fundamental material we need to understand for SN2, but there's still quite a few further topics that we need to cover to thoroughly understand SN2, and in the next video in this series, we'll proceed to one of those further topics dealing with SN2. Before we do that, let's do a quick review quiz. How would you define the term nucleophile? What's the exact definition of a nucleophile? I hope that for each of these questions you'll pause the video and come up with an answer. Well, here's the best answer. I hope you gave a two-part definition. A nucleophile donates electrons to join an electrophile. This is the best definition to learn for a nucleophile. Next question. Pause the video and define leaving group. Here's the answer. I hope you gave a two-part definition. A leaving group receives electrons to leave an atom. Last question. Pause the video and define electrophile. Here's the answer. I hope you gave a two-part definition. An electrophile receives electrons to join a nucleophile. You need to know these definitions like the back of your hand to succeed in organic chemistry. Now you can proceed to the next video in this series where we will introduce our next SN2 topic. Did you find this video to be helpful? If so, you can support the videos by making a monthly pledge of $1 or more at my Patreon page. You can visit my Patreon page by clicking the link on the screen or by using the link in the video description box. Thank you.